Jnanam paramam dhyayam. Knowledge is supreme.
Welcome to this course on Advanced Transition Metal Organometallic Chemistry. Today we are going to be discussing about a special type of organometallic compounds, namely the transition metal cyclopentadienyl complexes. Now, the field of organometallic chemistry per se as such relates to cyclopentadienyl ligand in a big way, because the field sort of developed or emerged around CP systems. Particularly, a lot of activities based on the organometallic compound in and around cyclopentadienyl ligand were undertaken in 50s and 60s with the aim of greater understanding about transition metal organometallic complexes, and also with the intention of generating various kinds of transition metal organometallic compounds. So, the field sort of developed synonymously with the development of transition metal cyclopentadienyl chemistry, and from that perspective today's lecture, which would be centered around transition metal cyclopentadienyl complexes, assumes significance, because these compounds by and large are synonymous with organometallic chemistry, and many people still sort of perceives these compounds to be the unadulterated examples of organometallic compound, and all of these probably can again be traced back to ferrocene kind of system, sandwich compounds, from where the organometallic chemistry or many more of the organometallic chemistry has its deep roots in. So, today we are going to be talking about transition metal cyclopentadienyl ligand, or in shorts they are called CP ligands. So, the easiest way of preparing these compounds starts from the reaction of cyclopentadiene with inherent nascent metal. For example, C5H6 plus potassium in benzene gives K plus C5H5 minus, along with generation of hydrogen. Now, this was done by Thiel way back in 1901. Now, one interesting aspect about organometallic compound is that many of the compounds were reported to have synthesized way long back, maybe a century or so earlier, but it was not until maybe a century or so later that people had found characterization techniques, or as well as evolved or developed synthetic protocols that would allow them proper isolation and characterization, as well as storage and stabilization of these compounds. So, some of the compounds might have been made earlier, might have found in many of the earlier literature or references. However, the understanding of them as well as the characterization of them came way beyond a century or much later. And the best example of that is Zeise's salt. The Zeise's salt was made way back in 1800, but their proper explanation of how olefin is bound to the transition metal, the forward sigma donation from olefin to the metal and metal back donation from the metal to the olefin, and was proposed by Dewar-Chert Duncanson in 1950s, and the structural characterization even happened in 60s or 70s. So it's kind of interesting to note that these compounds might have been prepared way back in time, but the proper appreciation and justification or explanation for these compounds came much longer, sometimes several decades or even a century later. Similarly, the reaction of a cyclopentadiene gives plus hydrogen. These was also exactly a similar reaction to the one that we had discussed, and this is this famous ferrocene molecule which was prepared direct from the cyclobutadiene with iron at very high temperature, 300 degrees centigrade, formation of the ferrocene and with the elimination of hydrogen. It can also be prepared by the reaction of C5H5 MgBr three equivalents of it with FeCl3 giving ferrocene plus half of C10H10 plus 3 MgBrCl. So this was reported by Persson in 1951. Now, at that point of time, there was a greater interest on the structure of ferrocene. In the hindsight, such debate made sense because there is no sigma type orbital available to make a direct sigma bond with the Cp ligand or Cp anion. So one is left to wonder that how does the aromatic pi cloud interact with metal orbital, and such kind of interaction had not earlier been observed in any other metal complexes. So given the fact that the synthesis of this ferrocene compounds was reported somewhere in 1950s, 1951 and 52, the explanation of the structure was given by Fischer in 1952, and it says that it is a double cone structure with the base of the cone represented by two Cp ligands and the metal being at the center, and this was based on structure analysis, and the structure of ferrocene was thus given by something like this. The magnetism showed that these are diamagnetic compounds, and this is obvious from the 18 valence electron count, 10 and 5e. So overall 18 valence electron compounds, and also from X-ray behavior. It is also found that these two Cp rings are in staggered conformations where they are not in eclipse conformation, so their orientations are exactly opposite what would be expected in an eclipsed conformation. So this was a very interesting report by Fisher, who really solved the structure of ferrocene and found that these two cyclopentadienyl ring are indeed flanking the iron in a trans fashion. Thus the hallmark of the structure becomes that it is a sandwich structure, and the dipole moment of this net dipole moment is 0. And that is because the iron Cp dipole moment each cancel each out in opposite direction, such that the net dipole moment becomes 0. At room temperature, the cyclopentadiene is sort of stays as the dimer the way it is shown over here, and this dimerization is formed as a Diels-Alder reaction. Now, upon heating at 180 degrees centigrade, the one performs thermal cracking or does a retro Diels-Alder reaction, or retro Diels-Alder reaction. Giving rise to formation of a cyclopentadiene. Now, cyclopentadiene generated can be deprotonated using sodium metal, giving 2 of sodium Cp along with the liberation of hydrogen. Can be stored under air moisture free conditions. So, sodium Cp is a very common reagent in organometallic chemistry. Here is a generic method from salt and Cp reagent. So, MCl2 plus twice NaC5H5 results in C5H5 2M. This is a very common solvent and a common method, and can be used in preparation of various kinds of BCP transition metal complexes, where M can be vanadium, chromium, manganese, iron, cobalt, and the solvent for this reaction usually are THF, DME, ammonia, liquid. Okay. This is sort of an example of salt metathesis or salt exchange reactions. Like instead of MCl2, one can use other salts as well. For example, this reaction of nickel acac with Grignard gives nickelocene plus twice MgBr. Similarly, dimethyl magnesium or di-CP magnesium can also be used for such synthesis. For example, MCl2 plus BCP2 Mg giving M plus MgCl2. This is very similar reaction of what we had just seen in the earlier discussion. And another example includes chromium chloride plus 3 of sodium M5 giving 5 whole 2 chromium plus C10 H10 plus 3 NaCl. Now, over here what one sees that chromium goes from plus 3 oxidation state to plus 2 oxidation state, and here is a reduction of chromium 3 to chromium 2 occurs. To facilitate that process, sodium Cp is the reducing agent, and the Cp anion gets C5H5 minus, facilitates this reduction and itself gets oxidized to produce this C10H10. Loses electron, becomes radical, and then dimerizes to give C10H10. So here we see sodium Cp acting as a reducing agent. Furthermore, the reaction with various kinds of transition metal halides, for example, tantalum pentachloride with sodium Cp leads to only replacement of 2 of the chlorides, giving eta 5 C5H5 whole 2 TaCl3, and then a subsequent reaction with again sodium Cp replaces the another 2 to give eta 5 C5H5 whole 2 tantalum eta 1 C5H5 whole 2. Similarly, for rhenium ReCl5 with sodium Cp, one gets eta 5 C5H5 whole 2 rhenium hydride. So, here also rhenium has undergone a reduction from +3, a +5 to +3. Over here it has undergone reduction from +5 to +4. The reaction of sodium Cp with 4D and 5D salts gives Cp metal hydride complexes or sigma bonded eta 1 bound Cp complexes. So, these are two interesting aspects that came to the fore, that sodium Cp not only can act as a reducing agent, but also can give rise to formation of metal hydride as well as eta 1 bound Cp complexes, along with the reduction the sodium Cp performs for itself. Similarly, the direct reaction of metal from cyclopentadiene M plus C5H5 giving M C5H5 plus half H2. M can work for lithium, sodium, potassium, as well as metal can also react with C5 cyclopentadiene at elevated temperatures to give plus hydrogen, and in this case this occurs for magnesium and iron. So, what does it say? It says that less electropositive metals reacts at high temperature or metal atom co-condensation conditions. Whereas high electropositive metal reacts immediately or readily with cyclopentadiene with the elimination of hydrogen. So, with this I would like to conclude today's lecture. In this lecture we have looked into the structure and bonding of cyclopentadiene ligand, the history of its origin, as well as various synthetic methods available for preparing these cyclopentadiene complexes. We have also seen that these compounds are extremely air and moisture sensitive, particularly of those of the more electropositive metals, and as one goes to the less electropositive metals, the reactivity or sensitivity of these cyclopentadiene complexes sort of decrease. Also, that is reflected in the conditions in which they are prepared. For example, for the one reaction discussed over here, the highly electropositive metal reacts readily, giving very sensitive ionic compounds, whereas the less electropositive metals like iron and all reacts at elevated temperature and to give a stable complex. So, with that I will conclude today's lecture, in which we have looked in depth at various metal transition metal cyclopentadiene complexes, and would continue a little bit more on this topic in the next lecture. So, with this, thank you for being with me in this class, and I look forward to being with you in the next class. Till then, goodbye.